Yes.
Fabulous. And I've been told that you are doing differentiation at the moment. Is that right?
Yes.
Super. Well, I'm obviously not Vlad. I'm standing in for Vlad today. My name's David Vaccaro. I'm a COMPOS tutor, and I'm going to look at some differentiation problems with you. And I'm guessing right that you are happy at the moment differentiating mostly polynomials. Is that right? Okay, right. You've done some trig as well. I'm going to focus mostly on polynomials today, but what I'm going to look at is slightly more involved problems, like you would see in a math or stat paper or something like that. So let us begin with this question here. So it says the cubic that, and then it gives an expression for a cubic, has a turning point that is a local minimum when x equals 1, precisely for which values of k? Okay, so put in the chat any thoughts about what you feel you would need to do for this question. So, right, we need to differentiate and make it 0. That's certainly going to give me a turning point. And what's the extra piece in the jigsaw to look about to see whether it's a local minimum? Yeah, so second order derivative will be positive. Now, I think this is not a particularly devilish example, but the thing which makes this question ever so slightly harder is the presence of two objects, x and k. Okay, and it's important to recognize that x is when we do differentiate, x is the variable, and k in any particular instance is a constant, but it's a constant that can vary. Okay, so it's temporarily constant, but then we look at different values of it. And it's just important to get the right terminology. Can anyone tell me the right terminology for a term like k that is a constant but can vary? Excellent. It is a parameter. Okay, so now we've identified what to do. The rest is a matter of technique. So we differentiate. So we do y dash is equal to 3 k x squared, subtract 2k plus 1 x plus 2 subtract k. Now what we want to do is we want to check whether x equals 1 is a turning point. So y dash of 1 is equal to 3k minus 2 times k plus 1 plus 2 minus k. And if we simplify, we get 3k minus 2k subtract 2 plus 2 subtract k, which is equal to 0. So we get the first kind of surprise. So we've got k equals 1 is always a turning point. Okay, but people are absolutely right. We want to now look at whether this turning point is a minimum. So we need to differentiate in order to do the second derivative test. So we differentiate the derivative. So we start by differentiating 3kx squared. So we get 6kx subtract 2k plus 1. And now at k equals 1, at x equals 1, because that was where the turning point is, we evaluate y dash 1, which is equal to 6k minus 2k minus 2, which is 4k subtract 2. So the question is, when is this minimum? If what's the sign of y double dash at a minimum? Okay, so someone said positive. So this is a minimum if y double dash is bigger than 0. Okay, and that condition is equivalent to 4k minus 2 is bigger than 0, which simplifies to k is greater than 1/2. Now, this is a little bit subtle. Okay. And this is kind of, you know, part of the point of the webinars to sort of train you in good techniques. Why is what I've written insufficient? I've not really written anything that's wrong. Yeah, no, someone said it's not precise, but there's a little bit of extra precision. Right, excellent. Okay, so it's difficult for the people watching the recording that they can't see what's happened in the chat. But someone has said that I need to look at what happens at k equals 1/2. Because what I've said is true, okay? That if the second derivative is positive, then there is a minimum. So what I've shown so far is that if k is bigger than 1/2, that implies that the turning point is a minimum. Okay, it's also the case that the turning point is a maximum if y double dash is less than 0. Okay, but at the moment, okay, if you look at my logic, I've only shown that if k is bigger than 1/2, that implies that the turning point is a minimum. That's all I've written up to this point. Now, to complete the proof, I should really try and show whether any other values of k give a minimum. Now, what I know is that the turning point is a local maximum, so not a minimum. Is a local maximum if y double dash is less than 0, which is equivalent to k being less than 1/2. But at the moment, okay, if k equals 1/2, okay, I don't actually have any information from the second derivative test whether it's a minimum, a maximum, or a point of inflection. So if k equals 1/2, the second derivative test gives no info. None at all. Okay, so what we should look at is we should look at the case k equals a half, and we get y dash in that case, so I'm just going to here, is 3/2 x squared minus 3/2 times 2, so that's 3x, plus 2 subtract a half, so that's 3/2. So that's, I can take out a factor of 3/2, and I get x squared minus 2x plus 1, okay, which factorizes as 3/2 times x minus 1 squared. Now, I can't use the sort of second derivative test, but how can I use this expression for the derivative to find the nature of the turning point at k equals a half? Yeah, look at numbers either side, okay? Or alternatively, look at the sort of sign of the first derivative. So if I think of the critical point, so the critical point is x equals 1. At x equals 1, the gradient y dash is 0. At every other point, it's positive. Okay, so if k is equal to a half, the nature of the turning point, so for k equals a half, we have a point of inflection. Okay, so the correct answer is k is greater than a half. Okay, now, as a maths teacher and as a maths teacher of students like the people on this program who are very able mathematicians and have a good mathematical insight, one of the things that I struggle hardest to convince them of is that what's inside this blue box is not enough. It's the right working. It leads to what turns out to be the right answer. Okay, but the logic was insufficient. Now, I think many people's intuition will be that if k is less than a half, we get a local maximum, and if k is bigger than a half, we get a local minimum. That at k equals a half, we kind of like have to go through the sort of barrier of being a point of inflection, but that is not clear. Okay, so this section turned out not to be sort of necessary, and you'd still get the right answer, but this is required for the sort of complete logic. Okay, now I don't want to kind of go down this I don't want to go down this line and you know, and make sort of nasty comments about people who study different types of subjects, because we're all friends. But I think you know, in terms of this argument here, you know, I think if you're really, you know, might convince a physicist, but for sort of pure sort of mathematics, mathematicians care more about the logic and would really insist on this argument on the right. So the question in the chat says, so what cases would there be where you need the complete logic to get the right answer? So in my opinion, well, I'll give you a sort of philosophical answer and then a sort of more practical answer. So the philosophical answer is that I think that in order to answer the question, show that it has a turning point that is a local minimum for which values of k, I would say philosophically, you've answered that question when you show that there is a set of values of k for which it is a local minimum, k bigger than half, and you have also shown that for all other values, it's not a minimum. It's a little bit like if someone asks you to solve an equation, that means finding some numbers which are roots and showing that those are the only roots. Okay, so I would not regard x squared, solve x squared equals 1, and then the answer x equals 1. I would not regard it as a solution, because while they found one number that works, they haven't found all numbers that work. Okay, the solution to x squared equals 1 is best done through the factorization. And once you have the factorization of two things multiplying to 0, you know that that is true if and only if one or other of those brackets is 0. So I would regard this as a solution to x squared equals 1, and I would regard this as incomplete. In terms of your wider question, Alistair, when, in what circumstances do you really want this complete logic? Okay, in A level you'll be fine. Okay, A level is not marked to a particularly rigorous high standard. And if you get the right answer and you haven't clearly used an incorrect method, you will be fine. For the entrance papers, so MAT, PAT, and in particular STEP, okay, once you get into the longer question sections, I think you can hit the point where they are marked to a more stringent and more sophisticated level. So that's kind of an immediate target. Longer term down the line, when you get to university, obviously the standards are higher still, and then it's good training if you show the complete logic. So I don't want to scare you, and I don't want you to feel bad. I think it's completely natural that when you do GCSE and when you start A level, if your teachers give you full marks for what's inside this blue box, it's completely natural that you will think that what's inside this blue box is all that you need to write. But I think one of the advantages of doing a program like COMPOS is to notice that there is that what is kind of passes for good A-level work is not always perfect. Okay, let's move on to the next question. So let fx equals 2x cubed minus kx squared plus 2x minus k. And it says, for what values of the real number k does the graph y equals f of x have two distinct real stationary points? So put in the chat, if you're keen, what you expect to do within this question. Otherwise, I'll just go through it without commentary. So yet again, k is our parameter. So we do f dash x is 6x squared minus 2kx plus 2. Okay, this is a quadratic equation. Okay, and this has distinct real roots. Okay, if and only if the discriminant is greater than 0. So the discriminant is b squared minus 4ac in normal notation. So this is my a, 2k is my b, 2 is my c. So we get b squared is 4k squared. 4a is minus 4 times 6 times 2. And we require that discriminant to be bigger than 0. So we want, that's a bit of a strange number. So we want k squared to be bigger than 12. And so now we just have a quadratic inequality to solve. And k squared is obviously equal to 12 at plus or minus the square root of 12, which is 2 root 3, and negative 2 root 3. So this k squared is bigger than 12 if k is bigger than 2 root 3 or k is less than 2 root 3. Okay, I appreciate I did that question very quickly. Okay, this is actually a math multiple choice question. So in the sort of pantheon of admissions test questions, it should be on the doable side. If you are happy with this question, and if you think I've got it right, I hope I haven't made any slips, but if you're happy with the pace and everything, put a thumbs up in the chat. If you weren't for any reason, then just put some questions in. Thumbs up, good. Thumbs up, good. Thumbs up, thumbs up, thumbs up. Fabulous. Okay, and I did that quicker because there's less gremlins in that question and there's no real logic. The only sort of logical word that I've used, which you, as you do more and more of COMPOS, you'll feel more and more comfortable about, is I've used this phrase, if and only if. Okay, so that covers this logic that you know, that it goes both ways, that there's distinct roots. If the discriminant is greater than 0, and if the discriminant is greater than 0, then there's distinct roots. So that's the only condition we need to check. Okay, let's move on to question number 3. Okay, which is a slightly more sophisticated question. So this is from a step 1 paper. And I will check later what year it's in. I think it's 1998. Again, put in the chat if you're keen what you think you would do here. Okay. But this is just a slightly more beefed up version of question number, well, the question before. So it says, sketch without calculating the stationary points, the graph of the function f of x given by f of x equals x minus p, x minus q, x minus r. So they conveniently give it in factorized form. So we know that this product is going to be 0 precisely when x equals p, x equals q, or x equals r. So it's going to equal 0 at precisely these 3 points, P, Q, and R. We're told that P is less than Q is less than R. We're not told that they're all positive, so P could be the other side of the axis. This is a cubic function, okay? So we know what general shape it's going to be. We can also see if x is bigger than r, then all of the brackets are positive, so it ends up here. So the graph must look like this. It then asks me to prove this very weird looking inequality. Okay. And I think this is one of the kind of things that as you look at more step questions compared to A-level questions, there's often like a little bit of a point of discontinuity where it's not clear how the first part relates to the second part. Now, this step question is relatively friendly because it tells me what to look for. It tells me to look for the quadratic equation f dash x equals 0. So I will do that. And the first thing I need to do is I need to open the brackets. Now, I'm going to open the brackets in a bit of a tricksy way. Okay. First of all, I know that I can get an x cubed term by taking an x cubed from each of the 3 brackets. If, however, I take an x from the first 2 brackets and then put it with a negative r, I get a negative rx term. If I take an x from the first bracket and then a negative q and a negative r, I get a x squared. I get a qrx term. And if I take the 3 constants, I get negative pqr. Now, I know this can't be the whole expression, but I can now think what the rest of the expression is, because if I get a negative rx squared term, it would be bonkers if I didn't also get a negative qx squared term and a negative px squared term, because the p, q, and r can just be interchanged. So I know that my x squared coefficient is going to be negative p plus q plus r. And if I get a q and an r term with an x, with a plus, I must also get the other products in pairs by symmetry. So I must get a pq and an rq. And of course, I'd get the same answer if I just open the brackets. So this is f of x. It then tells me to consider f dash x, which is 3x squared, take away 2p plus q plus rx, and then I'll get plus pq plus rq plus qr. Okay. Now, how am I going to relate this expression for the derivative and this graph together in order to give this inequality? So if you're feeling brave, put your answers into the chat. Okay. But this kind of stitching together of sort of 2 ideas in a way which is not necessarily obviously signpost is something which you will become more and more familiar with. So what can we see from this graph of the cubic? We can see that we must have a maximum here and a minimum here. Okay, so there is a maximum between P and Q, and the minimum between Q and R. So these are distinct turning points. But we know when turning points happen, they happen when f dash x equals 0. So f dash x equals 0 has 2 real and distinct roots. Okay, which implies that the discriminant is bigger than 0. Okay, so what we know now is that b squared, so that's 4 P plus Q plus R squared minus AC, 4AC, so minus 12 PQ plus RQ plus QR is bigger than 0. Okay, and now we don't need to do any more work. Dividing by 4 gives the result. Okay, so this is a differentiation question, but it calls upon a sketching of graphs and a sort of forming a connection between that and quadratic equations, and drawing a connection between quadratic equations and discriminants. Okay, I just invite you to put a sort of thumbs up in the chat if you're happy with that question, or put any questions in. I'm just going to look into the chat. Yeah, lots of thumbs up. Excellent. And there were some very good ideas earlier. People actually said Vieta's equation, which is a nice word to know. You'll meet these expressions for the relationship between roots and coefficients again. Okay. I won't spend too long on this. I won't spend too long on this question. I just want to show, I really want to focus on D. So it says the function f of x for x greater than 0 is defined such that f of x equals 1 plus x squared over x. So we can write f of x is 1 over x plus x. And now we can start to build up the sketch sort of piece by piece. Okay, so if x is small, so if x goes to 0 from above, 1 over x goes to positive infinity. X goes to 0, so f of x goes to positive infinity. So the first thing that we know is we know that the graph starts here. What happens when x becomes very large? Well, 1 over x goes to 0 from above, and we can say that f of x just becomes approximately equal to x. So what we have for very large positive x is we have something that is called an oblique asymptote. So here we know that the graph y equals x is an oblique asymptote, so the curve is here. Other things I know about the curve, I know that f of x would be 0 if the numerator was 0. But for all real x, 1 plus x squared is greater than 0, so there's no roots. Okay, so I know that it never crosses the axis. In fact, I know that it's always above the line y equals x, because 1 over x is always positive for positive x. And I can make an educated guess that it therefore looks like this. Out of interest, what would I have done if I drop the assumption now that x is bigger than 0? Is there any snazzy trick I could use to cover the case when you know, to know immediately what x would look like if x is smaller than 0? So if you feel brave, put answers in the chat. So I'll just do a numerical example. F of 1 is equal to 1 over 1 plus 1, which equals 2. f of -1 is equal to 1 over -1 plus -1, which is equal to -2. So wherever the curve was at 1, the curve at -1 is at the same value but negative. So we get the same shape rotated round. Okay, and then it says by solving f dash x equals 0, find the coordinates of the minimum point. So we get f dash x. So we differentiate 1 over x, so we get -1 over x squared plus 1. And so f dash x equals 0 if 1 is equal to 1 over x squared, which becomes x squared equals 1, which gives me x equals plus or minus 1. So we've got turning points here at those 2 points I found, 1, 2, and -1, -2. Okay, I wanted, as I mentioned at the outset on this question, to just try and have a little riff on the fact that differentiation is not the only show in town. So I'm going to sort of flip a big switch in the sky. Okay, and I'm going to turn calculus, which is differentiation and integration, off. Okay, so I'm going to pretend that Isaac Newton was never born. Okay, and we're back where we were before Newton. And what we're going to try and look for now is a calculus-free proof to find the turning point of 1 plus x squared over x. Okay, so I'll just give a minute on the chat to see if any suggestions come in. If you're watching this webinar on catch up, a little bit of time just to sort of pause the video and have a little ponder. Any suggestions? No. So I'm going to write something at this point, and I'm going to write something which very many of you will write. And when I was your age, I would probably have sort of written the same. Let's look at what I'm trying to prove. So I'm trying to prove that the minimum value of 1 plus x squared over 2 is 2. Okay. So I'm trying to prove, I'll write this in red because this is, wrong is too strong a word, but this is kind of wrong. So I want to prove 1 plus x squared over 2, sorry, 1 plus x squared over x is bigger than 2. Okay, I know that x is bigger than 0, so I write 1 plus x squared is bigger than 2x. Okay, because x is bigger than 0. I can now subtract the 2x. And now I can spot that the left-hand side is 1 subtract 2x plus x squared, which is 1 subtract x all squared, which is bigger than 0, which is true. So I'm going to put a little tick, true. Now, as I say, wrong is too strong a word. This is a little bit like the discussion of the first question. What is imperfect, logically speaking, about what is written here? No, I mean, X can, it's no, someone suggested that X can take any value. We are trying to find the minimum on X is bigger than, when X is bigger than 0. Okay, so this does establish, you know, this is, I have written here that this is restricted to the case when X is bigger than 0. Right, the latest things in the chat are much more pertinent. Okay, so what someone says, they say, you're proving it while already knowing the solution. And then someone higher up in the chat, and how do I scroll up the chat? Maybe I can't. Yeah, it says you're assuming 2 is true rather than proving it first. In terms of problem solving, okay, that's kind of what one does. One often has the answer. Or you might conceive of the question, show 1 plus x squared over x is bigger than 2 for x bigger than 0. The problem with the proof as presented on the left is the order in which it's written and the fact that there's no connections that are drawn between the different lines. So at the moment, we start with what we want. And then we do good maths. And then we reach something that is true. So our proof has had the flow of starting with what we want and then doing a chain of reasoning and reaching something true. Is this the right structure of the proof? No, the right structure of the proof starts with something that is true and goes back to what we want. So what we should have written is exactly the same thing. So this argument is lovely, but it should have gone the other way around. So it should have gone 1 subtract x all squared is bigger than 0. That implies 1 subtract 2x plus x squared is bigger than 0, which implies that 1 plus x squared is bigger than 2x. And if x is greater than 0, we have that 1 plus x squared over x is greater than 2 for x bigger than 0. Okay. When you solve problems, it's often quite more natural, especially with sort of show that questions. If this was in a step question, you know, for example, it's often easier to initially write the proof this way, but logically the flow of logic should go the other way. Okay, so you either just write the proof upside down, or you include the logical connections and you convince yourself that these implications actually go both ways and realize that the flow of logic going up is the proof, but it's safer to write this. Okay, what I'm really advertising, and I think this will improve your sort of written work, is the inclusion of these sort of logical symbols. Okay. You can tell I'm probably sort of a mathematician at heart, in that I'm concentrating on the arguments and the writing in this webinar, rather than just sort of cranking out the calculations. And I think part of the reason I'm doing that is I think a lot of A-level students at your, at your level, at your age, with your experience, are much better at doing the calculations than, you know, because it's more embedded in schools than these logical points. Okay, let's have a look at this question. So it says, prove that for x not equal to a, for all n in n, x to the n minus a to the n over x minus a is equal to xn minus 1 plus axn minus 2, and so forth. So we would just lay this out as probably it's easier to do the multiplication rather than the long division. But if I multiply x minus a xn minus 1 plus axn minus 2 plus a2 xn minus 3 plus ... an minus 1. So I multiply by the x, so I get x to the n. Then I get ax to the n minus 1. Then I get a squared x to the n minus 2, all the way up to an minus 1x. Then I start multiplying by the negative a's. And what I'm going to do here is I'm going to start doing those blue. So this is the sort of, this line of working is the sort of red products. And then the blue products I'm going to do on the next line. I wouldn't write red and blue products if I was writing this up. But I'm going to write the blue products on the next line. So I start with a negative a xn minus 1. Then I get a negative a squared xn minus 2. And I do this all the way to a negative a to the n. And I will have got a negative an minus 1x term when the a hit the previous term. Okay. And when I combine these terms, what amusing thing happens? Well, nothing happens to the xn, but all of these terms, all of these other terms cancel until I'm left with an a to the n at the end. Okay, there's loads and loads of other ways of writing it. I suppose my sort of beef here is just trying to write this in an orderly way. Okay, and now that I've got this product, if x is not equal to a, I can divide by x minus a. So I get x to the n minus a to the n over x minus a is equal to xn minus 1 plus a xn minus 2 plus a to the n minus 1. Okay, question. Have I gone mad? Okay. I was asked by Vlad, and you guys expected a lesson on differentiation. And I've included this question, which so far has been about polynomial expansion or polynomial long division. You could also conceive of it as being about a geometric progression. Yeah. If you regard this right-hand side as a geometric progression, you get that the common ratio is a over x. The number of terms is n, and the first term is x to the n minus 1. So if you sum the geometric progression, no, there's n. How many terms are there? There's n terms. So I get r to the n minus 1 over a over x minus 1. And then if I multiply top and bottom by x, I get an x to the n, so I get an minus xn over a minus x, which is equivalent. So I could even have done it by a GP. Okay, anyway, my initial question, have I gone mad? Okay, why can anyone tell me why have I included this question on a sheet about differentiation? Because it's interesting. Yes, so someone said it's interesting, but why is it of interest? Why is it of interest to differentiation? Yeah, it's looking, I'm getting better. I'm getting better ideas. Yeah, so someone's looked back at the question and looked at the part B, which invites us to think about what happens as x goes to a. Okay. Now, what happens as x goes to a on the left-hand side? Okay, so on the left-hand side, well, if I put x equal to a, I just get a head explosion. But if I put x equal to a on the right-hand side, I'm just perfectly happy. I've just got a nice polynomial. Now, what does this nice polynomial, if I imagine the graph of this nice polynomial on the right-hand side, okay, it's an n minus 1th order polynomial, so it might just wiggle about a bit. Who cares? But a is a perfectly polite and normal point. If I was to plot the graph on the left, you know, using a computer, the computer would substitute in all the different values. Okay, but the only difference is that at x equals a, you'd have this little singularity. So 2 questions. What happens to x equals a as x tends to a on the left-hand side? And why is that of interest to, why is that of interest in a webinar about differentiation? So this value here, this hole in the function, the first thing I can say is it's going to be equal in y value to where this polynomial on the right is perfectly well behaved. So if on the left I take a point very close to a, I get a point very close to this hole. So I get the limit as x goes to a of xn minus an over x minus a is what I get if I just replace x equal to a on the right. And if I do that, my first term is a to the n minus 1. My second term is a to the n minus 1. My third term is a to the n minus 1, all the way up to the last term, which is a to the n minus 1. So I get n a to the n minus 1. Okay. And so now what does this limit have to do with differentiation? Yeah, exactly. It's the proof of the power rule. It's the differentiation by first principles. Because this fraction, xn minus an, if I go back to my graph of y equals x to the n, if I pick a point A, and then I pick another point x, this rise between the 2 points is the difference between x to the n and a to the n. This run between the 2 points is x minus a. So this xn minus an over x minus a is equal to the gradient of the chord. Okay. So what I've done here, just using algebra, okay, is I know that x minus a is going to be a factor of xn minus an. So I can actually remove, in all other cases other than x minus a, I can remove that factor and get a nice polynomial. And this is, so this is a proof of differentiation of y equals x to the n at x equals a from first principles. Okay, I'm just going to ask a question, which is, I'm going to be really interested to know the result of this little survey. Okay. Can you just put in the chat whether you have seen at school either this proof or a different proof of the differentiation of powers by some sort of first principles argument? I'm just being nosy. I'm just interested to know what proportion of people have seen a proof and what proportion of people have just been told the rule. Yeah, kind of the people that haven't done any differentiation maybe absent themselves, but it's interesting. It's interesting to see that quite a lot of people have put the answer no, which is and quite a few people have said that they've seen a proof outside of school, but not at school. Some people have said a different one. There are lots of other different proofs. I like this one based on polynomial division. I don't want to labor the point too much, but there's some nice problems here of maybe a little bit more intense algebra, but to do similar things for fractional powers as well. For the people, for the people who are at schools that have taught differentiation and not taught differentiation from first principles, you're very lucky to be on you're lucky to be on a scheme like COMPOS, because that's one of the real advantages of a scheme like this, where you will see maths done properly, because a lot of it's not going to necessarily be the case that you need to know the proofs by first principles, but I think the proofs just give you this flexibility of thought to make the kind of connections that exam papers like Math and STEP kind of need. or, so for example, it's not at all obvious the connection between this fraction, the gradient of the chord, and this polynomial. And by seeing proofs, you just start getting used to seeing things in different eyes. Okay, if you like that example and are happy with it, put a thumbs up or a smiley face. If not, feel free to put any questions on the chat. Once I've seen a lot of smiley faces and an absence of questions, I'll move on to the next question. Cool, lots of thumbs up, lots of smiley faces, and so forth. Right, this is a nice little question. So it says, and this is a very good question for keeping tabs of what's a parameter, what's a variable, and so forth. So it says, the point AB with A and B in R and B not equal to A squared lies in the plane. And the point PXY lies on the curve y equals x squared. And then it says, find an expression in terms of x, A, and B for the value of AP squared. And then it says, use differentiation to find the value of x, which minimizes AP squared. Okay, so feel free to put in the chat what bit of mathematics you think you're going to use for part A. And part B is obviously tells us to use differentiation and so forth. But let's go through parts A and B. So natural place to start is a diagram. So we have this given point, which is AB. We have this curve, which is y equals x squared. And we have this point on the curve, which is xy, but I might as well call it x squared. And this point is A, and this point is P. And the question tells me to find AP. And the question's quite nice because it tells me to find AP squared. And I haven't checked the chat, but quite a few suggestions of the bit of maths to use have come in. So I'm hoping there'll be lots of people that are thinking of the bit of maths to use to find square lengths. Okay, and so we're going to use Pythagoras. So this distance is x minus a. This distance is b minus x squared. So AP squared is b minus x squared all squared. Oh my word. Plus x minus a all squared. Okay, so I need to open the brackets. Okay, so I get b squared minus 2x squared plus x4 plus x squared minus 2ax plus a squared. And so I get x to the 4 minus 2x squared plus x squared, so minus x squared. Minus 2ax plus a squared plus b squared. And so that's my AP squared. What I want to do now is I'm asked to differentiate. Okay, so I need to differentiate, so I get dAP squared dx is equal to 4x cubed subtract 2x subtract 2a. Minute, I've lost, I'm worried that I don't get a b anywhere. Oh yeah, so this is my, oh sorry, so this is minus 2bx squared. So I get plus 1 minus 2bx squared. Yeah, that's the only fix I need to make. Plus x squared minus 2ax plus a squared. And then here, so I get plus 1 minus 2bx minus 2a. Okay, and I get what type of equation do I get to solve? So I end up here with a cubic, equation. Okay, so I end up with the equation 4x cubed plus 1 minus b x squared minus 1 minus 2bx squared minus 2a. Okay, and what do we know about the solution of cubic? What do we know about the solution of cubic equations? Okay. Yeah, so there's going to be different solutions. Are the solutions of cubic equations easy to find? No. Okay. The solutions of cubic equations are not easy to find. Okay. And my computer's playing up a little bit, but I cheated a little bit. Okay, and while you probably sort of noticed that I sort of was stumbling over my words a little bit, and I was tapping away, because what I was doing was I was just using another program to try and solve this cubic that we get. Okay, and if you want to convince yourself that cubics are not easy to solve, this is the solution of the cubic that one needs to solve. Okay. And so this question is not easily soluble using the methods that you have. Okay, so this was a little bit of a kind of, not a trick question. Okay, but the real sort of question within this question is the next bit. And now a little bit of sort of physical intuition. Okay, so where on this curve y equals x squared do you think the closest point would be? So obviously you would go in a straight line, okay? At the shortest point, okay, I would argue, okay, that if you drew a circle around A and you drew the curve y equals x squared, you'd get the smallest possible circle at A, around A, that would touch the curve. So physicists amongst you, or just sort of geometers, using your intuition, can you tell me any relationship between this point A and this point P on the curve that minimizes the distance? What can you tell me about this line AP? So this line AP is the radius of the circle that touches the curve. Excellent. And so it's the line which is normal to the curve. Okay, because if I draw a tangent to the circle, it would just touch the circle at one point, and it would also be tangent to the curve. Okay, so part B, okay, use differentiation to find the value of x, which minimizes AP. This turns out to be really, really hard. Okay, and I set this to my sort of students as almost a little bit of a joke, because you get a nasty cubic. Okay, let's instead do question C, which is a little bit more doable. Okay, so it says, show that the line AP is the normal to the curve y equals x squared, which goes through A. So now this is a slightly more tractable problem, okay? But it's challenging because you need to think about how to use differentiation and how to find equations of normals, which will be something that you've done, but let's kind of do it. So what I'm going to do is I'm going to let P be the point P squared. Now I'm moving away from using x because I'm going to want to use x as my variable. Okay, so this is my curve y equals x squared. This is my point P squared. I want to find the normal at P. Okay, so if I do dy by dx, I obviously get 2x. So the gradient of the normal at P is the negative flip of the gradient of the tangent at P. So it's negative 1 over 2P. Okay, what I want to do now is to find the equation of the normal at P. So let us find the equation of the normal at P. Okay, so what we say is that y is equal to negative 1 over 2p x plus c. Okay, but this passes through the point p squared. Okay, so we get p squared is equal to negative 1 over 2p plus c. So c is equal to p squared plus 1 over 2p. Okay, so the equation of the normal at P is y is equal to -1 over 2p x plus p squared plus 1 over 2p, or which I can write as 2py is equal to 2p cubed plus 1 minus x. Okay, so this is the equation of the normal at P. Okay, and notice how it slowed me down, because if you have studied differentiation and at school, you quite often find normals at, tangents and normals. Notice how much more involved it is to do that with a general point with parameters. Rather, if someone had said to you, find the equation of the normal y equals x squared at the point 2, 4, that's your day job. At A level, that wouldn't even be a difficult question. Finding it at p squared is much more involved. Okay, now what did we decide was special about this point P, or this normal at P? So we decided that the P that we wanted in this question, okay, so the point P which minimizes the distance of AP squared, we decided that that normal that we want the point P where the normal goes through the point A. Okay, so we want the normal at point P to pass through the point A, which is the point AB. So how do I use that condition on this equation? If you feel brave, put answers in the chat. What condition is satisfied if this line here passes through the point with x coordinate A and y coordinate B? Well, we just want the point AB to lie on the line. Okay, so we want 2pb is equal to 2p cubed plus 1 minus A. And I think I've made a little bit of a mistake. Yeah, I've made a little bit of a mistake, because here, when I found the value of C, these P's cancelled. So this should have just been 1 over 2, which means that when I multiplied up by 2p, because I don't have this p on the bottom, this should be a p. Okay, so instead of a 1 here, I should have a P. Okay, so let's rearrange. Okay, so what does this imply? This implies that 0 is equal to 2p cubed plus p. And if I take the 2pb across, I get p 1 minus 2b minus a. Okay, so this is the condition here. So this condition here, this green condition, this is the condition that the normal at p squared passes through the point AB. Okay, if you're still following, very well done. Okay, where have we seen this condition before? Where is this familiar? This equation 0 equals 2p cubed plus p times 1 minus 2b minus a. I'll zoom out a little bit. Maybe it would help if I just relabeled p instead of being p squared. Let's relabel p as x squared. Okay, so in that case we have 0 equals 2x cubed plus x 1 minus 2b minus a. Now remind ourselves, why are we finding the point P on the curve y equals x squared such that the normal goes through A? What condition did we think that that point has where the normal goes through A? Well, if we remind ourselves here, we think that the normal at P goes through A if the distance AP minimizes the distance to the curve. Okay, but a long time ago now, we got a condition for the point P to minimize the distance to the curve. It was this derivative here. Now let's look at that. Okay, it's exactly the same condition here as here. So this condition implies that dAP squared dx is equal to 0. Okay, so what we've shown is the point P, which minimizes the distance, is the point which satisfies the derivative of AP squared is equal to 0, which implies that 4x cubed plus 2, 1 minus 2bx minus 2a equals 0. But that's exactly the condition that we got here, that the normal at x squared passes through the point A, AB. Okay, so part B, to actually find the coordinates of the points, we get a nasty cubic. But point C is doable, okay, and would be a nice university level question on differentiation. So what we've shown here is that the point P, which minimizes the distance from A to the curve, is also the point P such that AP is the normal to the curve y equals x squared. Okay, and now finally, here's a little vote. Okay, I won't ask you to prove it, but who thinks there's a general theorem that we can prove here? Okay, so is it always the case that the shortest distance from a curve C to a point A not on the curve is a normal to the curve which passes, is a point on the curve where the normal to the curve passes through A? So we'll take a vote, yes or no. So if I just draw any curve, and then I take any point, and then I look at the point on the curve which minimizes the distance, who thinks that it's a general theorem that the normal at this point would pass through A? We've proved that this is the case for y equals x squared. So let's take a vote if we think it's a general theorem. Okay, so we've got yeses, we've got lots and we've got lots and lots and lots and lots of yeses. We've got one which says no, it is only y equals x squared. Okay, let me draw a picture. Okay, so the shortest distance, if P is the shortest distance from A to the curve, then I can draw a circle. And I'm going to state without proof that the radius of this circle if I draw a because the circle touches the curve, if I draw a tangent to the circle, then it's also a tangent to the curve. So that what that means is the tangent to the circle is a tangent to the curve. So this angle is 90. Okay, so D turns out to be a true theorem. Given suitable conditions, which I'm not entirely certain what they are. Okay. Noticing the sort of difficulty of proving it just in the case of y equals x squared, okay, suggests that this is quite a nice challenge. Okay, so if you really want to go away for a challenge, maybe don't try and prove the general theorem straight away, but see if you can prove it for y equals x cubed, y equals x4, and then maybe get a proof for at least the general polynomial. Okay, but the working of this question was really a lot of differentiation. So differentiation to find this condition on the point which minimizes the distance, then quite a careful calculation to find the general the equation of the general normal, and then getting the condition of the normal that passes through the point AB, and then lo and behold, that turns out to be the same condition on the x value as the derivative is here. So even though this is just differentiation of polynomials, there's still an awful lot to there's still quite a lot to unpack within this question. And it's also quite a surprising fact that part B, which looks much easier than part C, is kind of not doable. But I really love this. I really love this question 6. I mean, it's hard and harder than the questions on the COMPOS sheets, but that's part of the point of the webinar, to look at really challenging questions. So I wonder whether there might be slightly fewer thumbs up here. Okay. If you do have a question about working for this question, please do put it in the chat. Or if you're happy with it, put a thumbs up. Oh, lots of thumbs up. Lovely. Do people like that question? Very good question to sort of say, like, how would there was a question in the chat which was, how would anyone do part B? Well, there is as you saw, my computer was able to spit out a horrible expression for the solution of the cubic. Okay, this really nasty expression here. Okay, so there is a formula for the solution of the general cubic. Okay, but it's not tractable, and it's not one which one could work with. So what is interesting is if you had on, in an exam, and this is more likely to be a university exam, if the question had said, show that the point P on the curve y equals x squared, which minimizes the distance to the point A not on the curve, then the tangent, sorry, the normal drawn at P passes through A. The interesting thing is that at the early point in the question, you might be tempted to try and find P, because in most sort of numerical examples, and the sort of numerical examples you would get at A level, you wouldn't get an equation that you can't solve. But if you try to sort of get an expression for P as the root of this cubic, that way madness lies. Okay, the only way to attempt this question is to show that the condition that minimizing the distance to point A and the algebraic condition that you get that the normal drawn at P passes through A, that these two things lead to the same condition on P. On the point P, but you never actually find P. So within this question, this part to find the value of X, this is a distractor. It's a very natural kind of thing to do, and you're so used in normal differential equations to be able to do it. But in this example, it's not something that you can do, and you just have to equate the two conditions. Any other questions about that? Yeah, excellent. And I think just one other observation to make. Now we can argue about whether it's a proof. But notice how part D, I haven't even attempted to sort of prove it in any algebraic way. But what I have at least got here is I've got a picture which gives the intuition. Okay, and I think this picture in this case is actually very, very, is very, very compelling. It is very compelling that the circle being a tangent to a curve is going to imply that the tangent is the tangent to the curve is also the tangent to the circle, which means that the radius of the circle lies on the normal. So it shows that while it shows the importance. So this sort of picture proof shows the importance of building up a kind of visual, intuition around differentiation, which points you in the right direction before launching into some algebraic proof of part D, which is liable to be horrible. You tend to find that really great mathematicians and really great physicists tend to have fantastic physical intuition. Okay, I had one last question which I didn't get chance to do, so I'll just leave this up long enough for you to take a screenshot, or if you're watching this on the webinar, to have a look at the problem. But I think that it's close to 8 o'clock, so I think this would be a good time to finish. So I'm just going to go back to the Zoom call, stop sharing my screen, and then just see if there's any final questions. And if there's not, I will say goodbye to people. Oh, there's questions in the chat. Would this be a question that we might get asked in an entrance exam? Not without a little bit more scaffolding, no. I think this is slightly more at university level. I mean, it's not, the individual components are not that hard, but the question is made harder by taking the structure, the structure out. But you saw when I was doing it that, like, it looks like it's going to be an easy question. It looks like, oh, you're just going to use Pythagoras, you're just going to differentiate, you're just going to set to 0. The issue is that you don't need to make the questions that hard before you start getting cubics. And once you start getting cubics, there's not algebra that you can, there's not algebra that you can do. The early questions were suitable for entrance papers and come either from sort of STEP or math. Okay, 3 new messages. Can every differentiable function be differentiated from first principles? I'm going to say in a sense, yes, because a function is only differentiable if that limit exists. I'm going to say, however, that you might not get a nice, there might be functions that you can construct which would not have a sort of nice sort of closed, which would not have a nice closed form. But certainly all the functions that you meet at school, sine functions, trigonometric functions, exponential functions, they can all be proved very much from, very, very much from first principles. And in later compost sheets, and whether you don't get them proved at school, we'll make sure in later webinars that you do get them proved from first principles here. And if you do maths at university, you really just start your differentiation all over again, and you do a lovely course called analysis, which just takes absolutely everything back to first principles. Okay, fabulous. Well, thank you so much. How do you prove that if 2 curves are tangent at t, that they share a tangent line at t? At this level, can we just state this without further proof? And would this proof be, yeah. So very good question, Elliot. So this thing about like the circle is tangent to the curve, so therefore the tangent to the circle is tangent to the curve. That is called hand waving. Okay. I'm not given a proof. I've not given a proof there. Yeah, and there would be a proof, and it would absolutely be the sort of thing that you would do in sort of first or second year analysis at university. But the fact I haven't proved it is not to say that that hand waving is not useful, illustrative, important in some, important in some sense. Because I think that when you do analysis, it's really hard to give a proof in analysis if you don't have some intuitive understanding of what sort of things are likely, of what sort of things are at least likely to be true. And a lot of students get very lost in analysis. They can't, because they just sort of move symbols around and they don't sort of have a sort of intuitive picture of what they're trying to prove. So what happens at university is that you tend to take methods courses and analysis courses. So you build up at the same rate technical skills of proving stuff at the same pace that you're also building up physical intuition for having a sort of feel of what's true, if that makes sense. The fact that the derivative of a turning point, the derivative at a turning point is 0, is probably something that you guys have not even proved yet rigorously. Yeah, you just have like an intuitive understanding, yeah, that if you go downhill, then at the bottom of the hill, it's temporarily flat, and then you go up. So you have a sort of feel that the derivative is 0, and that intuitive feel is, as important as a proof. Okay, let's see if there's any final questions. That last one was quite philosophical. No more questions, so I think we can all escape. Lovely to do this session with you. I hope you've enjoyed it. Yeah, thank you. Thank you so much. Good night, everybody.
Thank you.
Bye-bye, everybody. Right, I'm going to end the meeting for you all.